This is what I want to cover today. I want to cover active power, reactive power, the the basic confusion that you had, whether it's the amplitude, whether it's average. Let's look at that. Okay. So what I have written there is an equation for instantaneous power. Okay. What boils down to the basics is instantaneous power. If you're looking at it, when I say instantaneous power, power is a function at any given time. It is going to be product of voltage at that time, current at that time. This is true no matter what. And the unit of this is in fact just volt amperes. Instantaneous power agar aap dekh rahe ho, it's simply volt amperes, correct? Now, what I'm going to do is I'm going to substitute voltage as some sinusoidal function, because that's what we classically get from our outputs, right? The outlet there. So I'm going to write voltage at any time t is in fact some amplitude sine omega t. And what is this omega for me? What is this omega? This is linked to your frequency. So 2 pi f, if my frequency is going to be 50 hertz at the outlet, then it will be 100 pi, correct? Okay. And this, I'm starting with this because I'm saying this is my reference. Voltage at the outlet is going to be my reference. The current that is being fed through with this voltage, I'm going to represent as okay, the current I'm going to represent as again some magnitude, same frequency, because forcing function jo hai wahi. And then what is this? What is this? This is the phase angle. This is related to the load that you are supplying, correct? It is going to be linked to whether the current is leading the voltage, the current is lagging the voltage. What is that going to be a consequence of? Sorry? The nature of the circuit that you're feeding into. So is it a incandescent bulb? Then there will be no phi. Phi will be 0. If it is a motor, what do you expect that phi to be? It will be lagging, correct? And if you have a LED, then a mild lead is what you will see there. Okay? All good? Everybody okay? So this is what is linked to your power factor, in fact. All right? And so when I do a product of these, what I'm going to get is instantaneous power. Now, when you do that product, it's very easy to get the first equation. I want you to quickly write down for yourself where you get that first equation from. Okay? What happens here? Sine is, sorry? Yeah. So cos of A plus B minus cos of A minus B, correct? Ulta. Minus A plus B. Sorry. Yes. Sine A into sine B is, can somebody very quickly, sine of? Cos of A minus B minus cos of A plus B. Cos of A minus B. So that's going to be cos minus phi, but that will still, you could write it as cos phi. And then minus cos of A plus B. So that's going to give us cos 2 omega t plus phi. This is fine. So far so good, right? This, so your instantaneous power has some average value, and this you can instantly recognize. I could write it as VRMS, IRMS product now, because this 2 root 2 I can just distribute, correct? And that means I get my VRMS, IRMS, correct? Into cos phi. This is exactly what you recognize as active power, correct? So far so good. And But it's not just active power you're getting. This is getting added to another component, which is Vrms, Irms, a double frequency component. This is where you know your instantaneous power has oscillates at double frequency. So if you had a 50 hertz signal, if your voltage was 50 hertz, the current you will see in the circuit will also be 50 hertz, but the instantaneous power would be at 100 hertz, so on and so forth. 60 hertz in US would give you 120 hertz on the instantaneous power side. And this is where it's coming from, correct? All right. Now this, we know, we recognize this as active power. Where is your reactive power? What do you recognize as reactive power? Vrms, Irms, sin phi. But यहाँ पे तो sin phi दिख नहीं रहा है. So instead of doing decomposition this way, I could have further split these terms and did a little bit of rearrangement, and that rearrangement will give me something like that. I'm going to get Vrms, Irms, cos theta into 1 minus cos 2 omega t, okay, plus Vrms sin Irms sin theta into 2 omega t, and wo theta is the same as the phi I have used here. I'm sorry, I've switched between symbols. I apologize. Okay. Now, if you look at this, you know that the first component was your P1 type waveform, jo tha na, that's your first component. Okay. The second component is the P2 type waveform that you had. Okay. So your instantaneous power, you have decomposed into two components. The first component is the one that has an average of this, also oscillating at double frequency because it is a 1 minus cos 2 omega t term, correct? The second component has an average what? It averages to 0, okay? But it's also a double frequency component, okay? And what would be the peak for it? Its peak value is going to be Vrms, Irms sin theta, which is what we classically recognize as Q, reactive power. Okay? Everybody okay with this? Everybody okay? समझ में आ रहा है? How to go from that first equation to आपको सबको easily you should be able to see it. It's just application of sine, right? What about the second one? You have to decompose cos 2 omega t plus theta, or in this case phi. You would have to expand that, group similar terms, and you will get to the second equation. I'm going to leave that for you. Okay? That derivation is not as important. If you want, you could do it. It just fixes a funda in your ear, and more importantly, it gives you a mathematical intuition into reactive power, which personally I like. Okay, but it's up to you. But the equation does hold. That is a given. You could verify it. Now, from that equation, what I want you to focus on is the fact there is an interesting dichotomy in the way active and reactive power are in fact defined. Active power is an average value, and you can see that it's your first component. I'm going to write it here just so that this is what the first component is, correct? And okay, so this is what that equation would look for this specific system with that phi's and so on. So this is what we recognize as active power. This is what we recognize as reactive power. This particular waveform that you see here, what is it? The double frequency power component you see here, what is it? It is something that's oscillating at double frequency, and it is not zero average. It has an average. Its average is in fact the active power, correct? You could think of it as the component of power that is being fed to the resistive part of your circuit. And this one, on the other hand, is a double frequency component. It has an average of 0. So you could think of that particular power component as the component that is being fed to the reactive part of your circuit, correct? All right, okay. So in this particular question, this would have been your P1 and this would have been your P2 essentially, correct? All right, but more importantly, coming back to your question, now from here you can see that the P1, while it gives you what your active power is, it is not linked to the amplitude, it is linked to the average of P1. What is the average value that P1 is going to have over a time period? That is what is your active power. Whereas the reactive power will come from the second component, the component of power that is feeding into your reactive network, but it is not coming from an average because that power by design would average would be 0. So it's coming from a maximum value. Okay. Does that make sense? Everybody okay with this? Okay. Now, so this, if we were to look at the VRMS IRMS term itself, this, its units are volt amperes. This is what we think of as apparent power because this is the power that is apparently being supplied to the circuit. But the useful work is only being done by the non-zero average wala component, which is what we recognize as your active power, and hence P by S is the efficiency in some sense, right? Your power factor is telling you what part of the power you are supplying to the circuit, the apparent power you are supplying to the circuit is being used for some useful work, correct? That is what we think of as power factor, which is why we want power factors to be as close to 1 as possible, correct? All right. Q on the other hand is a maximum value, okay? And if you have a lagging power factor, that's simply indicative of the fact that you have inductive nature on the circuit that you're supplying. Leading power factor would be when you have capacitive nature on the circuit you're supplying. Make sense, everybody? This is basics being rehashed, okay? So when you put the S is equal to V into I complex conjugate, this is what I meant to write. This is a convention we have adopted just so that you can neatly break down your apparent power in terms of P plus JQ that you commonly recognize, and then P could be assigned as VRMS, IRMS, cos phi or cos theta, and Q could be assigned as VRMS, IRMS, sin theta. This is a convention. It's a construct, mathematical construct that helps engineers do a lot of analysis. Power engineers do a lot of analysis. Okay, all right. But you have to recognize this for what it is. It is a construct. It is not indicative that reactive power, the quantum of it, doesn't really indicate much other than the link to how much apparent power would be needed then, and hence indicative of the power factor per se. But it's something you cannot get away from, okay? In any big power network, reactive power is something you cannot ignore. By nature, there was one question: what would you have? Although there were people who didn't know whether conductance can or cannot be a part of that equivalent circuit, you all know that capacitance is something that you need to consider in transmission lines. Inductance is something that's going to play a role in transmission lines, correct? And if that's embedded in the way power is getting transferred across the network, that's going to manifest in some way or the other in how you're transferring power, and that reactive power is going to play a role. And today we'll look at it a little bit more, link it to how it affects power transfer or not, and hence think of how trades may in fact be improved or not with reactive power support, okay? So all of this is not just a recap of power engineering 1. I'm trying to reinforce some concepts just so that what you're doing here later in terms of trades and so on, you do understand the underlying physical system. Okay? All right. Now, classically, we could represent a power transmission line by some equivalent circuit. If you realistically look at it, what is a real representation of a transmission line? Like as real as it could get. What would be the correct way to represent a transmission line? Let's ignore the conductance part, but every small infinitesimal unit length of transmission line is going to have some sort of resistance, some sort of conductance, and some capacitance that's going to come into play, correct? And this block could be repeated, in fact, to represent as along the length of the transmission line how the electrical sort of circuit of the line would be. This is what we would call as the true model in some sense, and there are softwares which in fact break down the transmission line exactly into this. Each of this is some small delta x, and this delta x you would keep repeating till you cover the length of the transmission line. Okay, but you can imagine just how many meshes and how many nodal analysis you would have to solve to in fact get any sort of meaningful relationship for what is happening to the voltage and current from the sending end to the receiving end. So classically, when it comes to any sort of power transfer, you want to make sure you understand how much is the voltage you're applying at the sending end, what is the current you're supplying there to meet some particular voltage and current requirements at the receiving end. Okay, so you could say we are dominated by what your receiving end requires. The receiving end is a load you're serving. When you sign up under an obligation to serve that load, when you sign up, then you have to make sure you supply power of a particular quality. That means that 50 hertz should be close enough to 50 hertz for as long as possible. The voltage, if it was 230 volts, you have to make sure it's as close to 230 volts as possible or 240 volts as possible, correct? So that dominates your requirement. Now the person who's in fact consuming, it's an outlet. Now here I could put in a charger or I could put in an air conditioner. The charger is probably going to draw some very small current, right? But when I put in a air conditioner there, that's going to be a heavy load on it. But under both those conditions, ideally, I still want 220 volts there. Is that realistic? Is that realistic? So when I switch from a charger, let's say my phone charger, to a water heater there or an air conditioner there, is it fair for me to expect that 220 volts should remain as 220 volts? As a consumer, just because I flipped my appliance now, changed it, is the utility allowed to say, हाँ okay, geyser on किया तो अभी 220 नहीं मिलेगा, 200 मिलेगा? Sorry? With some margin of error. Very nice. With some margin of error, I'm not gonna go up to Adani and say, यार क्या 220 का 215 हो गया? No. But when 220 becomes 200, perhaps I may be concerned. And when 220 becomes 200 very, very often, when my neighbor also switches on his water heater and then, somebody else turns on an air conditioner, now I would be really worried, right? So it is his job to, in fact, make sure that I receive 220 volts as often and independent of how I consume, correct? That's what I sign up for. And that's what power quality standards would dictate. Power quality standards would say you have to try and give him the voltage under some, like some margin of error. You would have to be around 220, 230, 240 volts, whatever is that reference for us, nominal voltage and nominal frequency, correct? But is it really possible for that utility to, without doing any active measures, continue to just maintain 220 here, independent of how I consume. So if I was to switch from a charger to a water heater, which classically goes up to 2.5, 3, 5 kilowatts. So you're going from some, very small 40 watts to 5 kilowatts. That's a tenfold increase, no? Correct? Or 100-fold increase, I'm sorry. Is that, what is the utility actually doing then? It's still trying to give us quality power. It is obligated to give us quality power. And it has to do certain measures. What is it that it is doing? What can it do? For us to understand this, because this is basics of trade, no? That utility has signed up a contract with you, you are the customer. It cannot just willy-nilly give you, oh, आपने geyser on किया इसीलिए 200 था. Otherwise, we were ready to give you 220 volts, but वो geyser क्यों on किया? Utility can't say that, correct? Right? So what is it that it is doing? First things first, the utility needs to, you need to understand what is it that is happening, and understanding how power transfer works is in fact one of the basics for this. So what we are going to do is, we are going to look at this equivalent circuit, this transmission line, and just for simplicity, I'm looking at a very short transmission line, and the equivalent circuit for that transmission line, I'm not going to think of it in these delta terms, I'm just going to think of it as some lumped resistance, lumped inductance, okay? And on one end is my utility, which has some sending end voltage. So I'm going to say it's Vs, okay? And then there is a sending end current that it injects. This is the current I receive, and because this is a series element, of course, Is is equal to Ir, but I'm going by the classic theory, just you know that Is is equal to Ir, and this is my receiving end voltage, okay? All good? So far so good for everyone? Any questions? This is lumped resistance, this is my inductance, okay? Now, what I've drawn there is the classic phasor diagram as we know it, when the nature of this current is inductive. The kind of load that is getting supplied lags behind the receiving end voltage, okay? And so what happens is, this is my receiving end voltage, VR. I'm supplying some inductive load, IR, correct? ठीक है? I'm sorry? Okay, yeah, that's a good question. I'm sorry, I jumped over that part. I'll repeat the question. The question was, why are we ignoring the capacitance here? Why aren't we lumping the capacitance? Now, what is the genesis of the, why do we even consider capacitance for transmission lines? Where does the, sorry? Where does the capacitance come from? Anytime you have two conductors, capacitance is going to come into play, correct? That is where it comes from. But and so if you have two conductors and some dielectric medium in between, capacitance is going to come into play. The transmission line by nature, there's of course two conductors or three, if it was a three-phase transmission line, or you wouldn't even have ground as a conductor, you could think of it, right? And the dielectric is the air. It's not the best dielectric, clearly. So this is, at best, it's going to be a low capacitance. But when it's a long enough transmission line, you start seeing some effects of this capacitance, weak as its dielectric may be. But if it's a short transmission line, which is what I'm focusing on here, you would not have too much capacitance effect, so you can in fact ignore it. So the capacitance is so small in some sense that the associated impedance with it is going to be very, very, you could ignore it. Okay, it's almost like an open circuit, so you ignore it. That's what it is. Okay, okay, that answers your questions. Yeah, all right. Now, delta x doesn't ignore it, but that's the delta x model that we see. It's in fact for a very, very long enough transmission line in general. And what I've drawn here is an equivalent circuit. So you could take, it's a generic model in fact for any unit length. And then depending on the length of the line, you would in fact see some terminal relationships. And what I have drawn here is from those terminal relationships, when you derive an equivalent circuit, what would that look like? Now, in fact, just to complete, let's complete this discussion. Okay, so I don't have those equations here. Those used to be covered in a course we had earlier called Power Systems. So it's E334. That course doesn't run anymore. But I'll just very quickly cover this. So you know, the question you asked, this block would get repeated, okay? And this would get repeated on either side, all right? And this gives rise to what we call as the telegrapher's equations. These equations tell you voltage, so voltage at any distance x, and this x could be measured either considering the receiving end as the reference, so x equal to 0 is the receiving end, and then x equal to length of the line would be sending end. Or you could start this way, where the sending end is x equal to 0 and the receiving end is x equal to length of the line. It doesn't matter. So you can, in fact, based on this, you'll get a set of differential equations, okay? So you look at what would be voltage at, so if I start at x equal to 0 at the receiving end and x equal to L at the sending end, okay? You could have V of x here, and then this is going to be V of x plus delta x, okay? And you could you could do a circuit, essentially analysis of this, and come up with a set of equations that is going to help you describe the V of x and I of x. You'll get equations for both of these, okay? If you're interested, I could share the slides. You get a set of equations for this. You get this in terms of classic parameters of the transmission line, in terms of the R, the X, and the C, okay? You take these circuits and you could solve it for what happens at V of x equal to 0, which is what we call as VR, and I of x equal to 0, which will be our IR, and what happens at V of x equal to L, which would be Vs in this model, sending end, and then I of x equal to L, okay? And when you solve this, you will in fact get a relationship between Vs, Is and Vr, Ir, okay? This is your terminal relationship. It is not telling you what's happening at some distance x from the receiving end, or what is happening at some distance, one L minus x from the sending end. It's not telling you that, but it's giving you terminal relationships. If your receiving end needs so much, what is happening at the sending end? That's what it's telling you. Or vice versa. If you were providing this at the sending end, what would you receive? Correct? That is what it is telling you. Now, from this, okay, if you were to construct equivalent circuits, so you ignore all of these blocks in between and just try to come up with a model like this, an equivalent circuit, a circuit in terms of R, L, and C components that is giving you the same terminal relationships as what you would have otherwise gotten by solving these equations. Then you come up with some interesting models. And the classic circuit, in fact, is what we call as a pi model, okay? This is what that classic circuit looks like. This is a generic model that can be used to describe any transmission line. Any transmission line. You could go from solving these equations and getting the parameters of this circuit. What we observe is, when the line is short enough, this capacitance in fact doesn't have any role to play, and so you can ignore it in the analysis and treat it as if it's a series impedance. And that's the intuition with which I'm coming from here. Make sense, everybody? That completes the whole theory now. This is usually 3 to 4 lectures, but condensed version. All right? Okay. If you still need any more doubts on this, feel free. But I know there are people here who came in expecting not much power engineering. So I don't want to make it a lot of power engineering. So, yeah. So I hope you get the connection though. Okay, this is essentially, it's not as if it doesn't exist, but it's negligible enough for you to ignore it in your analysis. That's what it is. Okay, all right. Everybody okay with this? So far, so good. Now, let's go back to this then. So you have a short transmission line. In short transmission lines, the capacitive effect can be ignored. So you could treat the line, you could reduce the line to a series impedance. It's going to have resistance, it's going to have inductance. When it has both of these elements and it's supplying a particular kind of lagging load at the receiving end, what do you expect in terms of relationship between VR and Vs? What do you expect? So, if you were to just apply your Kirchhoff's voltage law here, Vs is going to be this drop plus VR. And this drop, you know that your sending end and receiving end current are exactly the same. So this drop is in fact going to be dictated by how much current you are supplying on the receiving end. The more current you supply, the more drop you are going to see. What is the nature of this drop? So I'm going to have a drop across the resistance. This is going to be my IR, R into IR component. I'm going to have another drop across the correct? So far so good? Yeah? And then I'm going to join all of this. I'm going to get my Vs. Correct? The magnitude, and I'm sorry, that's a much better diagram. You can see I'm going a little bit curvilinear. Apologies. The magnitude of the voltage at the sending end when you're supplying the lagging load at your receiving end is going to be higher. Correct? Everybody sees that. It's clear from the phasor diagram on the slides. It's clear from the attempt at phasor diagram I have here. Everybody agrees? Yeah? Would this be the same if I was supplying a unity power factor? If I, instead of a lagging load, it was not serving a motor, it was not serving a water pump, it was not serving a large air handling unit ka fan. It's just serving a large electric heater, furnace, big one. What would you expect? Would Vs in magnitude still be more than VR or equal to VR? What would happen? ड्रॉ करो ना. एक फेजर डायग्राम बनाने में कितना टाइम जाता है? या you could put it there, and then you could have, I mean, you just need to add all of these three components anyway. Drop across the resistance and drop across the, it doesn't matter. I could start with this and then add, I mean, I could very well do this and then add this. It's still going to give me the same thing. Sorry? This one? This is the drop across the resistance. There are three components. All good? Okay. This one. So I start with VR. Oh, before you have drawn, no? Tell me. So three options. VR equal to Vs in magnitude. No? VR less than Vs. And third one, VR greater than Vs. How many for option 1? Unity power factor chal raha hai. How many for option 1? Option 2? Okay. Option 3? Sahi jawab. Very good. Do I need to draw this then? Then let's just transition here. Unity power factor, you will still see that because there is still the inductive component that's coming from the transmission line itself, and that's going to have a phase difference introduced between Vs and Vr, and it's also going to have a magnitude difference introduced between them. Correct? Everybody okay with this? But instead of a inductive or unity power factor load, if I was supplying a capacitive load, now things get interesting. There's a possibility that I could in fact have my sending end lesser than my receiving end. Okay, all right. And what happens there is, so this is, I'm talking of capacitive load. So this is the nature of the current I have. So now I'm going to have drop across the resistance, drop across the, this is my current, and this is my Vs. This could very well be same in magnitude with Vr. It could even be lesser in magnitude than Vr, and that's going to depend on how much capacitive current I'm actually injecting. All right, makes sense? And this is in fact a way for the utilities to regulate your voltage. If you were in situations where you are where your loading is going to lead you to have significant sort of this one, you would have a large difference between what your sending end and receiving end voltage is going to be. I could simply do a power factor correction. What I could do now is, if this is the nature of my current, I'm going to install a capacitor here. Okay, let my receiving end current be whatever it is, but I'm going to add a capacitive current, correct? That is going to flow through this, and as a consequence, the net load that is going to be supplied to the receiving end may be different. It's not no longer going to be a lagging current. It may be a unity power factor type current, or it could be leading also, and in that way I could regulate voltage. Make sense? All right, okay, all good? Everybody okay with this? All right, so same circuit, let's stare at it now. From this, the next thing I want you to tell me is, what is the power I'm in fact transferring? Forget this capacitor, no longer there, just some receiving end current. What is the power that I'm transferring to the load? More specifically, PR, the power, active power at the receiving end. Could you tell me what that is going to be as a function of R, X, Vs, Vr, and so on? V? Who's saying this? Sorry, you. Oh, I'm so sorry. You were having, yeah. Vr, IR. So that's of course that's the basic key. But if I want it in terms of, so I can't control the I. As a utility, I don't have control over the I. What I could control, like I showed, is some, Vs and Vr pe mere paas control hai. Why? Because Vr I could put in a capacitor and try to make sure that my voltage is improved. I could regulate my voltage. Likewise, at the sending end, that's my control again. I could make sure my generator provides a voltage of sufficient quantity. So these are quantities I can control. IR is something you as a consumer will control, correct? So let's try to avoid IR into the equation. I want it in terms of your voltages, which are under the, usually influenced more by the utility actions than your end use actions. Although I did start off the discussion with saying water heater chalaoge या air conditioner chalaoge तो voltage पे क्या होगा, but ideally that is the counterpoint. In fact, the whole point there was that whatever you run there, the utility is still required to control voltage and make sure you in fact get 220 volts there, and it has mechanisms to do this by in fact using these sort of capacitors and so on. Okay, so coming back, what I want you to tell me is, could you tell me what the power transfer is, not in terms of the current IR, but in terms of Vs, Vr, and so on? How could you do it? So what is this? This is the apparent power for the receiving end. This we know, so I'll just call it SR for completeness, and this in fact is VR into IR complex conjugate, correct? Right? So I could just say that if I take the complex conjugate here, in fact, SR complex conjugate, which is PR minus JQR, is VR complex conjugate into IR. ठीक है? IR. ठीक है? And this IR, I will further write that as VR तो मेरा reference है, तो complex conjugate लो ना लो फर्क नहीं पड़ेगा. IR I could write in terms of VS VR divided by R plus JX, correct? That's it. Now where do I go from here? Where do I go from here? This VS, in fact, I've just written it in phase. By the way, all of this is in phasor form. I hope you appreciate that, right? So I could always write this in terms of this angle it makes with the reference, whatever be this angle. I'm just going to call it delta, correct? So I could say that PR is VR. I'll write this in the polar form, okay? Into VR and then of course this itself I could further write in terms of this is okay. Everybody sees this. कुछ तो याद आ रहा है. Power engineering 1, 2, something, huh? So far so good. Not Greek and Latin, I presume. Yeah. Okay. Very quickly, if you were to, I'm only interested in the real power transfer. Okay. So PR, I only need the real part of this product. And what is that going to look like for you? Can you very quickly just do some rearrangements and tell me? PR, you should be able to equate to the real part of this product. What terms do you need to ignore? What do you need to consider? And if you want to make it a bit easy, let's make it a bit easy. Huh? Large transmission systems, extra high voltage transmission systems, the R usually is much smaller than X. So you can ignore the R. R को zero मान के चलो. तो इसको zero करो, इसको zero करो, and now tell me what PR is going to look like. Again, ये zero कर रहे हैं not because it doesn't exist. It's small enough to be ignored, just like that capacitance. Okay? So, what would it be? Equation. जिसका किसी का फोन बजाता वो equation देगा इधर जल्दी. It's a very simple equation. हो जाएगा जल्दी जल्दी. You can come up to the board if you can't see it. Come. क्या है? ये मल्टीप्लाई हो जाएगा विद jx, so it cannot constitute for PR. क्या रह जाएगा? Come here, no. बोलो. Right. What do you think it's going to be? Delta divide by x. All power engineers ये रात को यही रट्टा मारते बैठते हैं. VS sin delta by x. इसी पे पूरा काम चलता है. And now this, in fact, you could use to argue a series capacitance also. I'll draw connections to that. One sec. उनको पहले आ जाने दो वो स्टेज पे. अब अबे ये नहीं आएगा, छोड़ो, जा वो. This PR is the real part of this. So the only thing that's going to remain, and this is DIY. आपको पसंद है ना रील्स वगैरह देखते होंगे, DIY ये भी करो DIY. This is going to be VR VS sine delta by X. Okay, it's a very special formula. It is derived under the assumptions that your resistance can be ignored. So in fact, this formula is power transfer over a lossless transmission line. Lossless क्यों? R0 करके चल रहे इसीलिए, ठीक है? And this is the formula, ठीक है? This is telling you the power transfer. So if you were not having any delta in between VR and VS, that means you can't push any active power. Your active power flow from the sending end to the receiving end is pretty much governed by how much is the phase difference between your sending end voltage and your receiving end voltage. And it is also dependent on the magnitudes there, correct? And it is dependent on the reactance of your transmission line. If you were to now put a series capacitor there, what are you effectively playing around with? ये कम हो जाएगा, ये reactance कम हो जाएगा, so you should be able to push more power across the transmission line. This is what one of your questions was. If I was to put a series capacitor here, what would it do? That series capacitor will help improve VR and VS relationship. Try to make sure they're as close to magnitude as possible. That will in fact also help us push more power. It regulates the voltage. It is going to avoid larger voltage drop between VR and VS. Okay? So that will also help improve your power transfer. Make sense? Still talking of quiz. Why these basics are important? How is this affecting your trades? Because while you care about these megawatts or kilowatts, and hence the megawatt hours and kilowatt hours they translate to, and you pay for that energy, to make sure this energy does get delivered through the transmission system, you may often require a capacitor, you may require inductor in some cases. Where is that going to come from? Why are they even in the business of providing support for your trades? These are all a part of what we call as ancillary services. These are support services that are going to help make the system work. They don't translate to, again, just like your P is the real part of the work done in the circuit, and that's, the P by S tells you efficiency and so on, but the Q is pretty much necessary. You can't ignore it. Likewise, whether we need this capacitor or not, what effect it is going to have, how it would help us push more power, you can't ignore this. This is of course necessary, and you need to figure out when you're doing trades how all of this is going to play out. Do you in fact require reactive power compensation or not? Are you going to require a voltage correction? Because if you don't do any voltage correction, it will manifest as a limitation on how much power you can push. Make sense? We started the first class with an example. If you guys recall, I told you 150 megawatt is the limit on that transmission line. How do operators decide 150 megawatt hai ya kya hai? They're going to look at these sort of equations, and they're going to figure out what are the safe limits, the safe delta separation that's okay from a stability perspective, what is the realistic sort of VR and VS we are going to see on the system by all the measures we know we could put in place for voltage correction. And based on that, they're going to look at this and then say, okay, for this corridor, this is how much power you could safely push. It's going to be a function of what corrective measures for voltage are in place, what they think from their intuition is a safe enough delta to maintain across the two sending ends and receiving ends, what they know from the line geometry, what that X is going to be, and so on and so forth, correct? That's how they in fact tell you what that operating limit is going to be. And yes, you could look at the whole thing simply as a number and say, हाँ ठीक है, operator ने बोला 150 तो 150 लेके चलेंगे, correct? But if you know your engineering basics and you know where it comes from, you can always go back and you can check, is this 150 a realistic limit? The NL there means no load, FL there means full load. And so the term is simply, basically, when we talk of voltage regulation in power engineering, we are really talking of, as you move from no load to full load, you're going to see a voltage drop, and that's how you measure the amount of voltage deviation and hence voltage regulation required. Okay, so in this particular setup, if you were to draw no current, then your Vs and Vr are going to be exactly same, which is why Vs is in fact said as Vr no load. Okay. Make sense? Any other questions? Any other doubts? I'm sorry, this delta is going to be a function of the phi or the theta here, but also a function of your transmission line, because you can see that this phasor addition will also play a role in the delta. So if your x and r were different, your delta would also be different. This delta, right? Yeah, yeah. No, so it would be, of course, so when it affects the capacity in the sense that you would want to maintain a particular delta. So if you were to allow a large enough separation, because either because of the current you allow it to draw, or the R and the X you have on the circuit, then that can lead to certain problems in terms of stability. So that is what I was saying. This delta usually, in fact, is only going to be 5, 10, 15 or something. But when you calculate capacity, you assume it to be quite large. It could be even 30 degrees, 40 degrees. This is what operator intuition tells you. And for a transient situations, it even could reach that. But you would ideally make sure that, typically the way these currents and the whole system is designed, it's usually going to be a much lesser than that. When you calculate the capacity, you would have a safety margin factored in, and you would say that, oh, 30 degrees tak bhi chal jayega, 35 degrees chal jayega, and that's how you would calculate it. Maximum delta allowed from the utility side, that's how you would calculate it. But it is not something the utility can decide. That's the point. The utility can say this is the maximum, and it may take measures to ensure that it never crosses that maximum, but it is going to be a function of your current that you draw and a function of your transmission line parameters. Yep. Any questions? Now, instead of this system, if you had the more classic pi model that we have, you have a capacitor distributed across. This is taking care of the actual line capacitance and so on. You can still, in fact, derive this formula. No, this formula. Okay. The only change is now your IR is going to be same thing, Vs minus Vr divided by R plus Jx, same thing that we had earlier, but it will also have this capacitive component that you have to minus out. But that capacitive component will not contribute to the product because it will be purely capacitive. So when it gets multiplied by Vr, it will contribute towards your QR. And so it will not in fact matter in deriving this formula. Your formula will still look pretty much the same as what you were deriving earlier. Okay? All good? So this, इसीलिए सब मेरे एमटेक के बच्चे, सब पीएचडी के बच्चे, उनको कभी भी ये क्वेश्चन पूछो, पावर ट्रांसफर VSVR by X sin delta, ये बहुत बायर्ट हो जाता है, because anyways, any which ways, this is what it will get reduced to. ठीक है? However complex your equivalent circuit is, this is what it will get reduced to. So this is a very powerful formula. I have a more generic set of derivation for this here also. For those of you who are interested, it will be a part of the notes. You could take a look at it. This comes from your transmission line. ABCD parameters were you guys introduced in your EMF? EM waves course. So if you are interested, the derivation exists. Otherwise, the genesis comes from this only. Okay? You could still look at it from this perspective and derive the same equation. All right. So very quickly, let's recap. What did we cover? Hopefully now you're a little bit more wiser about active power, reactive power. Hopefully now you know that power transfer across a transmission line is going to be a function of the voltages, but also a function of the phase difference, and more primarily governed by the phase difference. This, please remember, we'll revisit this when we go to other more complicated calculations of how much more power can we push given some trades and so on. All right. The last thing, which is linked to ancillary services, and this we'll almost cover towards the last few lectures, is the role compensation plays, the role voltage regulation would play, and this is linked to the broader umbrella of ancillary services. There are certain kind of support services that are always going to be necessary to make sure that all the trades you want to execute could in fact be carried out well in the grid, and you could still deliver quality power. Okay, and how those need to get remunerated becomes very, very challenging, because it is not meaningful work or useful work as we know it. It doesn't translate to any P, but it's very important to make sure you can in fact support P or transfer of P. And so we need to look at all of these things. This is what makes the course interesting, and this is what we'll be looking at as we proceed. Next class onwards, I'm going to start with review of very basic economics, concepts of utility, cost of production, short run cost, long run cost, so on and so forth. We'll cover a lot of these things very quickly so that we can start using then optimization to derive certain important pricing principles, and then we'll see how to link it to electricity markets. Okay, so next class, Thursday, we'll start with review of economics. Okay.